Audio Jungle. Audio Jungle.
Now we'll talk about the shaft arrangement. Okay, so arrangement of shafts. So it is nothing but arrangement of shafts. So that arrangements are basically two types of arrangement you have. Huh? It is nothing but here it is series, and the next one is the parallel. Okay, series and shaft in series and shaft in parallel. Shaft in series and shaft in parallel. Okay. So what do you mean by the shaft in series? So simple. If so shaft in series and shaft in parallel. Okay, so like if you remember that electrical current analogy, suppose this is what resistor, the one end of the resistor is what connected with the another end. Okay, this is R1, this is what R2. If you check current for this, so current will be same for both resistance. Okay, current will be same for both resistance, and there will be one supply of battery. Similarly for the parallel, if you remember, the electrical current analogy I am saying, so two resistance you have. If you check the analogy here, this will be the total current, this will be I1, and this will be I2, and this was the supply. So if you remember for the series, for series, here voltage drop will be V1, here voltage drop will be V2, and this will be the supply voltage. So this supply voltage will be sum of the drop of voltage across R1 and R2. R1 and R2 are resistor, V1, V2 are the voltage drop. But if you talk about the current, so current I will be current across R1, that is I1, and is equal to current across R2, that is I2. So here current is what constant, you can say, because only one path for the current, and current will be same. Whatever the current is what leaving, same current will come back here, and it will be same throughout the circuits because only one path we have. But if you talk about this parallel, so here for the current two closed path you have. Suppose this is A and this is what B. Here this was A and this was B. So to reach from A to B, only one path we have, so current will follow only one path. But here to reach from A to B, we have two different paths. This is what R1, this is what R2. So for R1 and R2, one path is what through R1, another path from A to B is through R2. So definitely current through R1 is I1 and current through R2 is I2. So whatever the total current I, this will be sum of the total current I1 plus I2. And obviously voltage, if you check this voltage, applied voltage is what across terminal A and B, and whatever the voltage drop across R1 it will be V1, and whatever the voltage drop across R2 it will be V2. So V1 and V2 both are connected across AB, and in fact this V is also connected across AB, hence this V is equal to V1 is equal to V2. So in one case current is what additive, like in parallel circuit current is what additive, so it is added I1 plus I2. If there are three closed path, so I1 plus I2 plus I3, like that. And if you check in series circuit, voltage is what additive. See, this voltage is what additive, but current is what same for both resistance. Okay. Similarly, here voltage is what's in parallel circuit. Voltage is what's same across both resistance R1 and R2. Because all the circuits, even R1, R2, R3, it is connected across A to B, and hence voltage will be also across A to B, and in that way voltage will be same in parallel circuit, and current will be additive. But in case of series circuit, current will be same for all resistance, but voltage will be additive. So this is the series and parallel circuit that you know very well. Now based on this, we have to check the shaft in series and shaft in parallel, so it will be easy for you to understand the things. Okay, now so we'll see here. Check, if you talk first shaft in what series. So shaft in series, so I'll draw the diagram in next page, so it will be better for you to understand the things. So shaft in series, so I can say this is the shaft here. Okay, fine. There is one more shaft is what connected with this, but it is series. So in series, end to end connection means this shaft is what is started from A to A and it is ending at B. So another shaft will be starting from here. So it will be like, so this is the another shaft. So two shaft you have, A to B and B to C. All right. So this is first shaft is what support connected here. It is at point A. So you may get this type of the arrangement, or sometimes in few books you may get this also. So your assumption is what it is circular shaft, so that you need to take care. Rest you can draw like this also, no problem in that. So two shafts here, it is connected A to B and B to C. So A to end to end connection is nothing but called series shaft. Okay, shaft in series. So if shaft in what series, then what will happen? So if you apply torque here, at suppose this end here, if you apply torque here in case of the series, so torque is what T is analogy to the current. So torque T is analogy to the current I. It's an analogy. So in case of series, you have seen that current is what constant or not. See, current I is what constant in case of series circuit. So this torque will be constant now for both. Okay, for both, I mean for A to B and B to C. So you can say here in this case, this torque in shaft A to B will be torque in shaft B to C, and this torque will be same for both. I mean, if number is what increasing, like 2, 3, 4 shafts are there and all in series, so this torque will be constant across the all the shafts. So hence we can say this torque is what constant. That first point you need to remember. So what is the conclusion here? Torque is what constant in series combination or series arrangement. What is the next? The next will be the angle of twist. Okay, next will be the angle of twist, and that angle of twist is nothing but theta, which is also called angular deformation or angular twist. So this angular twist will be the sum of both. Here you can say the angle of twist will be theta AB, and here it is theta BC. So first point is what this. Second point is what? Angular twist. What it is called? Angular twist. Okay. So this angular twist, whatever in shaft A will be, this is the proof also. Proof not required, as I told you. Proof is not required. It is proof also. You can prove this. So whatever the total angular twist, it will be the theta, and theta is what for whole shaft, that is theta AC. This is nothing but theta, you can say, for the whole shaft, and it will be the sum of both AB plus sum of this AB and BC. All right, AB and BC, this will be the total angular twist. All right, this is the series shaft. Now so theta is the analogy in series circuit. It is the voltage, which is nothing but V. So check in series circuit, voltage was additive, V is equal to V1 plus V2. If you recall this, so what was the theta? Theta in terms of the, if you check the formulation, so if you remember, this theta is nothing but theta per unit length, or angular twist per unit length. Okay, angular twist per unit length sometimes. So suppose this length is what you can say L1, and this length is nothing but L2. So angular twist per unit length, if you write, then it will be d theta. If you write for the complete, d theta by, in any length you can take d theta by dz. Suppose if you are writing in terms of d theta by dz, that is the length per angular twist per unit length. So it will be d theta by dz for AB plus d theta by dz for BC. Why I am saying this? Because if you remember the formula, tau by R is equal to T by J is equal to G theta by L. Okay, so if you check here this formulation, what is the, from this two combination you take, what will be the theta by L? So from this combination, theta by L will be what? It will be T divided by Gj. Okay, so if I say theta by L is constant, that means T by Gj is what the value of the angular twist per unit length. This is nothing but twist per unit length. So for series shaft, this twist per unit length will be added. I mean, twist per unit length for AB will be different, and twist per unit length for BC will be different. Why? Check here, T is constant. Here T is constant, but why this theta by why this theta by L is what changing? Check here, why this theta by L is what changing for A to B and B to C? Because of this J. J is the polar moment of inertia, because for AB diameter will be capital D, and for this it is small d. So J will not be same for A to B and B to C. Got the point? G is the material. In fact, G is the material property. Okay, G rigidity modulus. Maybe material is what same, maybe. So G will be constant, it's okay. But what about J? J will be changing by, because diameter is what changing. Or many times this G also changing. Suppose this is made, shaft A is made by aluminum and shaft B is made by steel. Just for example, I am saying. So G will be changing that time also. Okay, so don't think like theta by L will be theta by L, which is nothing but twist per unit length. Because torque is constant, so this will also be constant. No. Check the formula. Theta by L is nothing but T divided by Gj. Here, this value, fine. Anyway, so this is all about the shaft in series. So 2 points you got. What are the 2 points? This is the points. Point number 1 is the torque, which is constant. Torque, which is constant for the shaft in series. Second is the angular twist, or you can say twist per unit length. Okay, so this value will be additive. So this is the analogy of voltage in series circuit, and this is the analogy of current in series circuit. Okay, this is shaft in series, remember it. Now we'll go for the next, which is called the parallel. So
Sir,
yes, shaft in parallel. Okay, so in case of shaft in parallel, so how the shaft is what parallel, what will be the diagram? So in different book you may get different diagram, but this is the very usual diagram what I'm giving here. Okay, if shaft is what parallel, then that means the both shafts are at fixed end. You can get in this way also, check. Okay, so this is what parallel shaft. If you check the diameter here, so this is the axis about which you will have a torque. Here the inner diameter, and this is the outer diameter, capital D, and this is what, small d. This is the length of the shaft. Okay, so now fine. Or another diagram also you can draw for the parallel shaft, and it is nothing but fixed at both ends. Okay, so this is also diagram you may get in few books. This is the one shaft, this is the another shaft. Both ends are fixed. Remember, this is the axis for the shaft. Both are the fixed end. Here for this you can say a torque is what acting like this, and this torque is nothing but you can say torque T. Okay, so this end is fixed. Okay, and this is also fixed. So if you are applying torque here, so resisting torque you will get here at this uh, uh, end. Okay, you just say this is what A, this is what B, and this is what C. So at end A you will get resisting torque because it is fixed. So resisting torque means in this way you will get. So just say at this end torque is what, T1. Okay, T1 direction I am showing, because this magnitude will not be equal to this torque because both ends are fixed. Yeah? So don't say whatever the torque applying here at point T, this will be the same at A. Not possible. Why? Because both ends are fixed. So whatever the torque you are applying at mid, it will be distributed at both ends. And here also you may have a resisting torque you are applying in this direction. So resisting torque will be acting in this way. And here this torque is nothing but T2. T2 you can say it is nothing but TC, and T1 you can say it is TA, and T, this is T at B will be EB. So here now we'll go with this. In fact, for this also, if you say total torque you are applying T, so inside one shaft and other one upward shaft will be there. So here 2 shaft, you can say this is the outer side, so it is 1, and inside it is T2. So for this case also, T is equal to, you can say, total torque, which is nothing but T1 plus T2, because whatever the torque you are applying, so this torque will be transmitting from one shaft to another shaft. So total transmission will be distributed in both shaft. Understood or not? So whatever the total shaft you are applying, that torque will be transmitted to one shaft to another shaft also. That means it will be distributed. So total summation of the torque applied distributed, suppose one shaft is T1, other shaft is T2, so this sum will be equal to total shaft. And here also nicely you can understand by the second diagram that torque applied T is nothing but TB, applied torque is nothing but T at point B, which is also called TB, and this will be distributed in two parts, which is nothing but T1, that is also called TA, plus in C it is TC. So in both diagram, in this way you can understand. So what is the total torque here? It is T1 plus T2. This is the one conclusion. Okay, so total torque will be the you can say torque is additive here. So in parallel circuit, what is the additive? It is current. So check the parallel circuit. So in parallel circuit, what is the additive? It is current. So torque is what additive here, hence it is analogy of current. And already in series circuit also I have given this. Sorry. Fine. Now check at this end it is suppose fixed, and here also it is fixed. So what will be the deflection at point end point? It is A and it is C, we just say. So what will be the deflection or angular twist? So angular twist at both ends, because it is fixed also, so you can say angular twist at both ends will be the same. Okay, angular twist at both ends will be same. So in this case, what value you will get? This is about the torque. This is about the torque, this analysis. Now what about angular twist? If I say angular twist, that means angular twist per unit length. So this angular twist, because both ends are fixed, so whatever the twisting will be in one shaft, the same twisting will be another shaft, because it is fixed, it is clamped, you can say. So you can say now whatever the twisting, that twisting will be constant. Okay, twisting will be constant here, so it will be theta, you can say at this is T1, so here twisting will be theta 1, and here it is T2, so here twisting will be theta 2. So this is also, you can write d theta by dz at point, you just say A to B. If you want, you can write A to B is equal to d theta by dz at point BC. So this is what? This is analogy to the voltage. In parallel circuit, if you check, this is analogy to the voltage. So so angular twist here, it is constant. For single marks they are asking this, so always remember this. Okay, now this is done. The next very important part is the combined effect. Separately we had seen the bending stress. Now you have seen the, bending moment you had seen separately earlier. Bending moment in beam you have seen. Twisting moment in shaft you have seen. Separately you had seen, like in beam there was no twisting, hence that was pure bending. In shaft here you have seen no bending, only twisting, hence it is pure torque, pure twisting or pure torque in shaft. But now we are going to mix both. Now you are going to give the torsion is already there in shaft. Now you are going to give the bending moment also. So what will be the effect and what will be the formulation now? Okay, that is important because in examination they had asked. Okay, so now you are going to apply both, I mean bending as well as twisting. Okay, so here it is. Next topic, which is nothing but combining bending and torsion in shaft. Okay, so if I say bending, that means bending moment. If I'm saying torsion, that means twisting moment. Okay, why there is the twisting moment, that already I have discussed, but let me write again. Why there is a twisting moment? It is due to shear stress. It is due to shear stress. Why there is the bending moment? It is due to normal stress. It is due to normal stress. Okay, all right. Now definitely if you apply bending moment, so or if because of the shear stress, it doesn't mean because of the shear stress only twisting moment will be there. Because of the shear stress, sometimes bending moment also there, but that time due to shear stress only twisting moment will be considered, because twisting moment will be predominating over the bending moment when it is shear stress. Okay, similarly because of the normal stress you are considering only bending moment, but it doesn't mean because of the normal stress twisting moment will not be there. In fact, because of the normal stress twisting moment also, but bending moment will be predominating condition when you are applying normal stress over the beam or shaft compared to twisting moment. That's the reason due to normal stress only bending moment will be considered, and due to shear stress only twisting moment will be considered. Okay, this one is very clear to everybody, right? There should not be any confusion. Now here you are going to check the like all the story I have given to you. Till now I have not even started principal stress, but formula I will give to you, and I'm believing that you are aware with the principal stress. At least in your graduation you had seen principal stress stain, and after this definitely principal stress lectures will be started. But here direct value of the principal stress formula I will give: major, minor, if you remember, major principal stress and minor principal stress. Okay, maximum, that, and minimum. So that formula directly I will be using here. So now here bending moment M and torque T, if will apply the principal stresses set up in the shaft, and can be shown to be equal to those produced by an equivalent bending moment, and certain values will be denoted by ME, because now you are considering bending moment and torque both. So we'll write equivalent bending moment. If I say equivalent bending moment, means bending moment and torque both are there. All right, you should aware with this. Now how to draw the diagram for this? So to check, this is the shaft now, and for this shaft we are going to apply the both, I mean bending and twisting moment both. So this is what shaft here. Okay, not correct. So now we can take, I mean 2 points you can take. Okay, so axis is what here, this is the axis. So for the twisting moment, already I have given for the twisting moment, it is around the axis. So if it is around the axis, so I can say we have a torque here, this is around the axis, and along the axis, that means twisting moment and bending moment. Obviously, if I say axis, we have, suppose this is the one axis, this is the another axis, you say z axis, so your bending moment will be acting here, and this is nothing but m. This is the m, which is nothing but bending moment. So for the shaft here, both twisting moment and bending moment we are getting. So this is t is the twisting moment and m is the bending moment. Bending moment is what, along the axis, okay, and twisting moment is the around the axis. So this is what, along the axis, and this is what, around the axis. Now in this case, if you check both thing, I mean the value of bending stress, because bending moment we are considering, so bending stress will come into picture, and we are considering the twisting moment, so shear stress will come into picture. Okay, then only you will be able to write the equation for the principal normal stress. Okay, so directly we can give the formula, but 4-5 steps we need to write, so better we'll write this. Okay, so now if you go for this section, so I can say the diameter for this shaft is nothing but we can write here, this is what, capital D. Okay, now so if we write the first bending stress, okay, or that is called also a direct stress for this, because we are writing bending moment, so definitely normal stress will come. This normal stress also called as direct stress. Might you heard about this direct stress, and this shear stress also called as, sometimes you might have tangential stress. So these terminology are important. Okay, different terminology you are getting now. So check for the any circular beam, if the applying load is what P, because you are talking about the bending moment here, so definitely here I was saying because you are talking about the normal stress, so because of this normal stress definitely will have a bending moment. Here you are showing, so this normal stress you have to show here, and this normal load will be normal stress, or you can say this normal stress will come because of the load. And what is the load? Load is nothing but load P, that is the axial load. Because of the axial load you will have a normal stress or direct stress. Now you know that standard formula. Suppose this is the bar here, okay, this is the bar here, okay, and this on this bar load is what, acting P, and the cross sectional area of this bar is nothing but, this is the cross sectional area of the bar. So if I say what is the normal stress or direct stress, so you will say it is nothing but load divided by area. So this is nothing but normal stress or called direct stress. Okay, this is called direct stress or normal, because of this direct stress into that distance, perpendicular distance will give the bending moment. So that is the overall idea. Okay, if it is acting on the axis, so if you talk about the bending moment, so this bending moment will be the load into perpendicular distance. So overall idea is what, here you may have a maximum direct stress and shear stress for this element. You can take any element, cross section you can take, and for that you can calculate. So here directly I'm just going to write the formula. So it is nothing but called direct stress or called normal stress here. So it will be sigma x, and it is nothing but 32. This is the formula. Actually with the formula it will come pi d cube plus, because of the loading you will have a p by a. Okay, if you, how this come, you know very well, it is nothing but sigma upon y is equal to m upon I. With the help of this formula, this bending stress, this value will be coming, bending stress. This is the value of bending stress. Okay, bending stress. And p by a, as I told you, because of the axial loading you will get p by a, that is also the stress. So this is the direct stress. Second is the shear stress. So the shear stress you can say tau xy or only tau. So how it comes, tau by r, that formula you know. What is the formula? Tau by r is equal to T by J. Yes or no? If you use this formula, then you will get tau, which is nothing but shear stress. I can write tau xy, and this value if you solve, even in previous class also I had written this formula, how it comes, pi d cube. So simply you write the value of J, which is nothing but polar moment of inertia for this shaft. If you write, then you will get. Now what will be the principal stress? That is called normal stress. Okay, and what is the maximum shear stress? That is the job you are going to do here. So formula you know very well. For the principal stress, direct formula I am going to use here. This is nothing but principal normal stresses, which is nothing but sigma 1 and sigma 2. Sigma 1, which is nothing but maximum normal stress. This value is nothing but sigma x, because you are considering y value here. It is sigma y is what, 0, only sigma x you have. In y direction you do not have. It is not a bilateral stress, it's only unilateral. So sigma x you have, sigma y will be 0, hence it is sigma x plus sigma y by 2 plus, in this formula, sigma x minus sigma y. If you remember principal stress, this is the formula, square plus tau xy. Okay. Now what you will write, sigma 1 is equal to, this is nothing but sigma x plus 2 divided by sigma x divided by 2 plus tau xy. So with this formula you are aware, you had gone through in principal stresses 10 in your strength of material subject in your semester, so it might be you are aware with this. Now what is the sigma 2? So it is called minimum normal stress, also called minimum normal stress. So this value will be sigma 2 is equal to the same formula you have, instead of plus you will put minus sign, rest everything will be same. So sigma 1 and sigma 2 you got. Now what is the maximum shear stress? So maximum shear stress, now, so what is the maximum shear stress? It is tau max. So tau max formula is what? It is sigma 1 major principal stress minus minor principal stress. If you solve this, check the previous sigma 1 and sigma 2 you have calculated, take the minus sign, so sigma x will be cancelled out. What you will get? Plus minus, only root value you will get, sigma x by 2 plus tau xy square. So this is the value of tau max. Okay, this is the value of tau max. Fine. Now maximum shear stress you got here. Now you are considering the both. I mean, this is the formula which is already you have seen your principal stress strain chapter in strength of material. Based on this, okay, we have a sigma x now. This sigma x value we have. What is that? See, sigma x value here we have written, it is 32 m divided by pi d cube. 32 m divided by pi d cube. Okay, and similarly plus p by a. This is the value of the sigma x, and this is the tau xy. What is the value of tau xy? 16t divided by pi d cube. Okay, so instead of this sigma x and tau xy, if you place it, so you will get the value of both, called maximum shear stress, which is nothing but sigma 1, and maximum shear stress. They are asking this in examination. So how to write this? So based on so this is the formula. Now we'll go for the maximum principal stress in terms of this m and t. So instead of sigma x and tau xy, here this is the maximum, value, this formula. So here you need to keep this value of sigma x and tau xy in form of m and t. Similarly here this is the maximum shear stress. Okay, so for this formula also you need to transfer this formula. I mean, sigma x and tau xy you can transfer in terms of this m and t. That is the requirement. Okay, so what will be the maximum principal stress and maximum shear stress? So here I will write maximum shear stress in terms of m and t. Okay, m and t. So what will be the sigma max? So this value is nothing but 16 upon pi d cube in bracket m square t square. Okay, this is the sigma max. This formula is very important. Similarly, we have to, because this is the final conclusions you need to remember. Similarly, we have a maximum. This is the maximum principal stress. I have written normal stress, you can write maximum normal stress, and this normal is also called principal. Okay, if normal stress you will differentiate, so one value will get maximum, another value will be minimum, so it will be called as a principal. So maximum principal and minimum principal stress. So you are talking about the maximum normal stress, that means maximum principal stress you are talking. Similarly, you can write maximum shear stress here, maximum shear stress. Okay, so this is nothing but tau xy, and it is also in terms of m and T. So what is the tau max? Is equal to 16 divided by pi d cube m square plus t square. So how you will get? So all the steps I have written. See, this tau max you have calculated here. So sigma x and tau xy, you just replace this value, so you may get this result. Okay, you check, something will be cancelled out and somehow this value you will get. And similarly this sigma max, from where you will get this sigma max? From this formula. You just keep this sigma x and tau x value. Okay, fine. Now if you check this, after getting sigma max and tau max, we need to write the equivalent bending moment, which is called the combination of the m and t. I told you what is the equivalent bending moment. So equivalent bending moment, basically if you talk, if both I mean for any shaft which is subjected to simultaneous application of bending moment m and torque t, the principal stresses set up in the shaft and can be shown by equal to those produced by an equivalent bending moment, and it is obviously denoted by ME. So ME, if you say equivalent bending moment, so that will be the combination of M and T. I mean, you can replace both M and T, only one moment will be there, that is the equivalent bending moment. Okay, so that is the replacement of M and T actually. So what is the equivalent bending moment? So here I can write next the equivalent bending moment. Equivalent bending moment, that is also denoted by ME, and similarly we can get equivalent torsion also. So what is the equivalent bending moment here? Okay, what is the equivalent bending moment? So it is nothing but ME. This is very important formula. Actually 4 formulas are there, and all 4 formulas if you remember, then you will able to solve the problems. So equivalent bending moment will be the combination of both m plus m square t square divided by 2. Similarly we can get equivalent twisting moment, which is nothing but denoted by TE, which is nothing but m square plus t square. So actually if any shaft which is connected with the bending moment and connected with the torque, connected with the both, any shaft which is subjected to both bending moment and twisting moment, then this can be replaced by the single equivalent bending moment ME and single twisting moment, which is nothing but TE. So this is the final analysis when any shaft which is connected with the or subjected to the bending moment and subjected to the twisting moment, both if it is there, then this will be the analysis. Okay, so this formula is what basically used when both bending moment and twisting moment are applied to the shaft, then this formula will be used. Otherwise if only bending moment is there, then formula you have. If only twisting moment you have, then formula you have. But if both are applying for the shaft, then this formula you need to remember. So how many formula you have now? See, these 2 formula we have derived basically. This is number 1 and this is 2. Okay, this is the formula you need to remember, and this one is the equivalent value, which is 3rd, and this is the 4th. rest, it is basic. Like this principal stress strain, when I will teach you, that time I will derive and I will tell you. And you know this formula already, you have used in your strength of material, right? So now for today's session, up to this, you need to keep with you and check previous year gate question they have asked based on this. So I will solve the problem also at the same time. Next class will have the analysis of the thin section. Okay, for the thin wall analysis, we have to check the shear flow because of the shear stress because of the torsion. If torsion is what applied to the thin cell or thin wall, then the analysis of the shear flow we have to check.